Welcome everybody to this workshop on Kubernetes and ARM with OCI. I'm Jeevan Joseph. I'm a solution architect at Oracle, and I'm joined by my team of product managers and other colleagues from Oracle, including Greg, Mickey, Adal, and Sherwood. They're all on the chat. So if you have any questions, feel free to ask any questions using the Q&A feature, and we'll be able to answer that. This is a hands-on session, so a lot of you would have received instructions and a free trial offer from Oracle to set up a cloud account. We will be using that account during this workshop. And if you have not signed up yet, or if you have to sign in, now would be a good time. The whole workshop is structured in such a way that I'll be giving you an overview about this workshop and what we'll be doing and some context setting in the first 10 to 15 minutes. So that would be a good time for you to sign into your cloud accounts if you haven't already. And then we will start creating a Kubernetes cluster and working with ARM-based workloads. So let's quickly take a look at the agenda. So we'll first do some context setting. If you're new to Kubernetes, we'll just give you the Kubernetes 101, the very basic primer. Some of you might already be very familiar with Kubernetes, so please bear with me. This might be a little bit redundant for you. Then we'll talk about supporting multiple architectures in Kubernetes. And then we will move on to the hands-on workshop and do a quick Q&A. But during any time in the workshop, if you have questions, please feel free to use the Q&A section in Zoom, or there will be a couple of spots inside this hands-on where we are waiting for stuff, and we'll open up for questions along the way. So before we get into Kubernetes clusters with ARM, let's first take a look at the basic motivation, right? In a traditional system, we deploy applications on persistent hosts or VMs. Now, over time, these hosts will take on various configuration changes to support these applications. And in most cases, there isn't really a good record of what configuration exists on what host. So effectively, these hosts become really, really important, right? And eventually, one of these hosts is going to fail, and the application owners are going to scramble to find and fix that host, because you really have to fix that host, because you can't really create something quite like it because you don't know what's something quite like it. VMs can address this problem somewhat, but there are still a lot of application dependencies, that are beyond the host level. So one way that people, control this is to move to a container-based paradigm, right? So, like I said, when failures happen inside hosts, you don't really have a recourse, right? You have to kind of like fix that host. Containers can address this to a large extent by encapsulating the application, its configuration, its runtime environment, all of that into a container. Now, what that gives you is much better portability, right? So when something fails inside a container, you just need to recreate that container. And that is a much easier ask than trying to recreate a host and all its configuration files and all its dependencies and all the things that were installed and configured on that host. Because a container encapsulates all of this stuff, it is very easy and very portable. And containers are fairly mature at this point. They use very, very mature features in Linux, like C groups and namespaces, to isolate processes and limit resource usage. But containers still force you to deal with hosts, because containers have to run on hosts. It's a lot easier to move containers around, but you're still dealing with hosts. Like, you still need to manage hosts. You still need to start containers on hosts. You still need to know what's running where, and if something fails, how to restart it somewhere else, right? Now, Kubernetes, on the other hand, takes this to the next level. It automates the container management. So in Kubernetes land, we try not to think in terms of hosts, but rather in terms of capacity, right? We think in terms of the fleet. We think in terms of the total capacity that we have. Like, I have, 128 cores or 500 cores and X amount of memory, like 3 terabytes of memory. And that's what I need for my applications, right? So it does not matter what hosts that these capacities available on. Kubernetes can move our containers around based on the status of our fleet. So when something fails inside Kubernetes, Kubernetes itself will notice that, hey, I'm supposed to have, you know, uh, this particular application running. It does not seem to be running anymore. So I need to restart this application or create a new container that represents that application somewhere else. If a node fails, Kubernetes will notice that and it'll automatically move everything that was running on that node to some other node. So all of this enables much better application development and much better velocity in the development lifecycle. And that's important because when we move from a traditional paradigm to a container-based paradigm, this ability to build and test applications really fast is super important. Now, before we get into the ARM specifics, let's look at the Kubernetes cluster itself. Um, Generally speaking, during this workshop, we're going to use a Kubernetes cluster that is provided by Oracle. It's called Oracle Container Engine for Kubernetes, or OKE for short, and it's a CNCF compliant managed Kubernetes platform. So very broadly, Kubernetes has a set of components that manage and control the cluster and its workloads. This is basically grouped into two broad groups, control plane and the user plane. And the nodes where these control components run on, they're called the control plane nodes. And in a managed Kubernetes service like OKE, the control plane nodes and the controller components are managed by the cloud vendor. So these include things like the Kube API server, the controller manager, the scheduler, the cloud controller manager. The cloud controller manager is an interesting one because, while every Kubernetes cluster has these components, the cloud controller manager is the thing that makes it work with a specific cloud. So everything that is cloud specific is encapsulated into the cloud controller manager. So in Kubernetes, when you say, hey, I want to expose my application using a service of type load balancer, and when you deploy that definition or manifest into OKE, it creates an OCI load balancer. When you take that definition or that manifest and deploy it to Azure or AWS, it creates their version of a load balancer, right? That logic is encapsulated inside the cloud controller manager. So effectively, the application definitions that you're building become incredibly portable, and it's the components inside the Kubernetes cluster that manage the vendor-specific details. The control plane also includes etcd, which is a distributed key value store, and it contains and manages all the configuration data and the application definition, the manifests, and all the data and configuration for your cluster. On the worker nodes, we have the actual capacity. So, the control plane nodes simply run the control components, the management components, and in a managed Kubernetes service, the control plane nodes are typically owned and managed by the cloud vendor. And some cloud vendors charge a fee for it. Oracle does not, but the actual nodes or the capacity on which the applications run, that is usually managed and owned by the user, right? And generally, you can have many types of nodes. And then specifically in the case of OKE, we support our users to mix and match any types of nodes. So we have support for ARM nodes, we have support for x86 nodes, nodes with GPUs, and so on, right? VMs, bare metal machines, you can mix and match any of these things. Nodes of the same kind are usually grouped into node pools. So node pools, you can think of node pools as a way to scale your capacity as well. So, when you're trying to manage capacity and you think that, okay, it's at night, nobody's using my application, so I don't want to, use 50 nodes. I can scale down to like 10 nodes, right? Node pool is the thing that determines that scalability. So When you want to add capacity to your cluster, you expand a node pool or grow a node pool. When you want to shrink your cluster, you contract that node pool. Um, and again, like I said, the control plane nodes and the control plane components are usually managed by the cloud vendor, and the worker nodes and the actual capacity, right, where the applications are running, that is managed by the users. So when it comes to using ARM in the enterprise, right, it's still about the applications. Kubernetes makes that transition easier by giving you a lot more control over that transition than ever before, right? So that increased velocity of development that I talked about initially, that basically helps us prototype things faster, test things faster, validate things faster, roll out things faster, and if it doesn't work out, roll them back faster. So Kubernetes and containers can really help with that transition. When you want to make that slow transition, you don't have to like flip a switch and go from x86 to ARM, right? I mean, that's a big step for most enterprises. So what we have seen happen is enterprises try to introduce ARM into their ecosystem very slowly, right? They'll add a small node pool, and in that small node pool, they'll assign some non-critical workloads, right? When that's going on fine, they'll start adding assigning some of their work to the ARM node pool, mix it with the x86 node pool, and slowly taper off on the x86 usage, right? So the application challenges are still the same, right? To really evaluate the impact of introducing ARM to your server-side applications, you need to consider the changes that change will usually involve, right? It could include runtime environment changes, things like a different version or a different runtime for runtime languages like Java or Python. Or it might include actual application changes for applications that are optimized for a specific CPU architecture. If you're using a compiled language, it will generally involve cross-compiling your application against multiple architectures and producing multiple binaries, right? One that works on ARM, one that works on x86, and so on. However, containers can absorb most of this complexity, and we have automation that can build, cross-compile, and set up these application dependencies. Applications are then packaged as containers, meaning that their entire runtime environment and that entire configuration is captured and it is made into a portable unit, right? And container images are architecture specific, which would make sense because the actual binaries and the runtime dependencies would be different, right? But container image registries, the repositories within which container images are stored and act as a vending machine of sorts for container images. These registries usually have multi-architecture support, right? Within container image land, this is usually called a manifestless support. But what this basically means is the registries can usually provide a single URL like Docker Hub or docker.io/library/WordPress. It's a single URL, but if an ARM machine is requesting that image, you get the ARM version of that image. And if an x86 version is requesting that image, you get the x86 version of that image. So it's kind of like a facade, if you will, right? So image registries can, solve most of those architecture dependent things. But at the end of the day, when you use Kubernetes as a transition platform for trying out ARM and moving into ARM-based workloads in your enterprise applications, it makes that transition a lot easier and smoother because you have that ability to rapidly prototype, rapidly test, rapidly, undo if you need to, right? So with that context out of the way, let's actually start, building a cluster and trying out some workloads. So the whole workshop will first log into our cloud infrastructure account. I hope all of you have your infrastructure accounts created at this point. Otherwise, you can follow along with this lab. This is going to be a live lab, so you can follow along. And the QR code and the URL that was in the chat window, that'll basically take you to a GitHub repository where this whole lab is explained step by step. So if you want to do it offline, you could do that as well. For this entirety of this lab, we will be using purely the Oracle Cloud Console. So let me go ahead, change over to my browser, and let's get started. So here I have already logged in to my cloud account. This is what OCI looks like if you have not seen it. And you'll find our Kubernetes services under developer services, and it's the first thing under containers and artifacts. I generally like to just go to the search bar and just search for OKE, and it should pop up pretty quickly. So I'll go to the container engine for Kubernetes page for the service, and we're going to create a cluster. So before I do that, let me quickly pause and see if there are any Q&A or any questions. If there are none, I will proceed. I don't see any. So at this point, we can create a cluster. You'll also already see that I have a couple of clusters created here already. We'll probably be using one of them, but let's walk through how to create a cluster, right? So when you try to create a cluster, we generally offer two main ways of creating a cluster. One is called the quick create workflow, and the other is called the custom create workflow. For this exercise, we will use the quick create workflow. What this does is it basically assumes a lot of sensible defaults, and it'll create a lot of the prerequisites for us. The custom create is really useful when you want a lot more control over how the cluster is created, how it is networked, how it is attached to your existing cloud resources. For the purpose of this workshop, I'm not going to care too much about any of those things. And I'm going to focus more on, how we can quickly create a cluster, right? So I'll launch this workflow. And basically what it's going to ask me is a name for the cluster, a compartment. The compartment is a construct inside OCI that basically lets us compartmentalize our resources and apply policies to it. So it's a construct through which you can apply permissions and access control, and also organize your resources. So I have a compartment by my name. So I'm going to create my resources in my compartment. And you get to pick Kubernetes versions. We have support for multiple versions of Kubernetes. So you can pick, I'll pick the latest version of Kubernetes. And there are a couple of choices in terms of the endpoints and the worker nodes. Without going into too much detail, I would say the API endpoint basically determines how accessible your cluster is. If I have a public endpoint, I can reach my cluster from anywhere. I can reach it from the internet. I can reach it from my laptop. I can reach it from anywhere. A private endpoint basically means that the cluster itself is only reachable from inside the virtual network in your cloud tenancy. This is much more secure, but for the purposes, again, for this workshop, we'll use the default of using a public endpoint. Again, the worker nodes themselves, the actual computers that run your workloads. I'm going to put them in a private subnet or in a private network. I don't really need access to those actual nodes from the internet, so that is fine. Now comes the most important thing, right? The shape. So as you can see here, we have shapes, we have multiple shapes. And maybe this, it's helpful to explain this a little bit. Anything that starts with a BM, BM stands for bare metal. So you're basically getting an entire server. So, the BM standard A1, and A1 is our ARM-based instance. So the BM standard A1 bare metal server, if I choose that, I get 160 CPUs and 1 terabyte of memory, right? I mean, that's kind of overkill for this lab. So I'm going to use a virtual machine. And you'll see that we have a bunch of bare metal machines here and a bunch of virtual machines here. So I'm going to use the A1.flex virtual machine. So the A1.flex is quite unique in the sense that it is an ARM-based, server built with the Ampere Ultra CPUs, and within these VM shapes, I can actually choose the number of CPUs I want and the amount of memory I want. This is fairly unlike any other cloud vendor where you have to pick a specific shape, right? I mean, so that one CPU, two CPU, 4, 8, 16, 24, or something. I mean, what happens if you want a 27 core machine, right? I mean, with our A1 Flex shapes, you can get a 27 core machine if you wanted, right? I'll keep things simple here. I'm just going to create a one CPU 6 gigs instance, but I'm going to create 3 of them, right? You can change this number, and if you had used um, the um, the cloud trial that was sent out through this ARM Dev Summit, I believe everyone who signs up actually gets $500 of credits, and the even after the trial expires, you still get to keep 4 full ARM cores and 24 gigs of memory. So if you will still have access to that forever. That is never going to expire, and you will never get charged for it. So let me choose 3 nodes, and we can take a look at the advanced option. I'm not going to change anything here. I'm just going to accept all the defaults here. So we have advanced options. Hang on. We have advanced options that specify custom boot volumes, enable image verification. Again, not going to get too much into details here, but we'll keep it high level and just quickly review what we need to what we have selected so far. So as you can see, we're going to create a cluster, and it's assumed some defaults for some CEDA blocks here. There's going to be one node pool. It's going to be an A1 shaped node pool. And you'll see that to create the cluster, we have 2 options. There's a create cluster button right there, and that's a quick way to create a cluster. You could also save this as a stack. That second one is really interesting. I'll just call out what that is, because when you save it as a stack, what OCI is going to do is it's going to generate a Terraform configuration. A Terraform is a tool to manage infrastructure as code. So it's going to convert all these settings, all the definition of this cluster, if you will, and save it as a piece of code, right, that you will have access to. What that enables you to do is you can create this cluster later and recreate it and destroy it any number of times, and you will get the exact same configuration every single time. If you want the same cluster in another region or in another compartment, or you wanted to have a staging in production, they have to be absolutely the same, right? This is a great way to do that. So let me just go ahead and create this cluster. And you'll see that most of the resources are getting created now. All the networking and the security lists and the node pool definitions are getting created. But the cluster creation is a asynchronous process. So once this is done, let me close this, and our cluster is in the creating status at this point. It's going to take about, I would say, about 8 to 10 minutes for the cluster to finish creation. And here you'll see that, okay, the cluster itself is getting created. Along with that cluster, we are also creating that node pool, right? Once the cluster is created, we will have the ability to go and add another node pool here. So rather than wait here, unless there are any questions, I think I will move on to a cluster that I've already created and see what that looks like. So this is a cluster that is in the active status. I created it a couple of weeks ago. And one thing you'll notice is that I have 2 node pools here. And this is the configuration that we want to create for this particular lab or this particular workshop, because we are going to simulate how to move from x86 nodes to ARM nodes, right? So in the example, just the cluster that I just created, I chose a ARM-based node pool. I chose the A1.flex shape. Now you could come here and add a new node pool and make sure that it is an x86 based shape, right? So other than the A1, all the other instance types that are available here are x86 based machines. Anything that is VM.standard, they're usually Intel based machines, and anything that is standard.e is an EPIC or AMD based machine. So you could choose an E3.flex or an E4.flex type machine for it. But make sure you add a second node pool. Let me just quickly go back and see if our cluster is still created. No, it is still in the creating status. So once the cluster is created, you will have the ability to add more node pools to it. So in my case, I have two. And for the purposes of this lab, you should also create two specific node pools, one x86 and one ARM. And in this case, the second node pool, pool 2, is the ARM-based one, because you can kind of tell it by looking at the version of Oracle Linux it's running. It's running the 7.9 AR64 version of the operating system. So now, once a cluster is created and you've added your node pools, right? We need to actually access the cluster and start interacting with it, right? And you could always set up your local environment, your terminal program to, install the tooling and get connected with your cluster. I have a setup myself, like I have my unique setup. But for the purpose of this lab, and when you're getting started with Kubernetes clusters on OCI, I highly recommend you take a look at the Cloud Shell. The Cloud Shell is persistently available in the top ribbon on the OCI console or the UI. And when you click it, you're going to get a full-fledged terminal environment inside your browser. The interesting thing about this is that it comes pre-installed with all the tools and utilities, all pre-installed and pre-configured for you. So it includes all the tools like the OCI command line utility, kubectl or kubectl utility to interact with clusters, and Docker and a bunch of other things. So it's going to take a couple of minutes for that environment to come up. And once it does, we'll be able to access our cluster directly from the Cloud Shell. And like I said, this is just a convenience feature. So if you prefer to access your cluster from your local terminal on your laptop, that's fine too. The instructions on how to access your cluster is provided from the console itself. So, there is a button here called Access Cluster. And once you click that, you have the ability to see, how do I set up access to this cluster, right? So if you're using your local terminal, this is the instructions you follow. And if you're using the Cloud Shell, it's pretty simple. It's just 2 steps. I've already launched the Cloud Shell. I'm just going to copy this command and run that. And the command specifically will notice that it is using the OCI CLI, which is the command line interface for the OCI cloud. And it is running a subcommand called create kubeconfig. And it's passing in a cluster ID, and it is setting some other parameters like the type of endpoint that I'm going to use, and the token version I'm going to use, and the region this is in, and so on. What this means is that to connect to a Kubernetes cluster, you need to configure the Kubernetes client or the kubectl or kubectl client. And it keeps this configuration in a file called the kubeconfig file. It's generally just called kubeconfig, but it's usually stored inside your home directory in the .kube directory under a file just called config. It could be anything. You can change that location. That's fine. But this OCI subcommand generates that configuration for you, and it's going to generate it specifically for this cluster that we just created. So I'm going to copy that, and I'm going to come and paste that in here. I will most likely have a config file already there. Yeah, so basically told me that there's an existing config file there and the new config has been merged to it. So uh, since I'm going to be using the Cloud Shell quite a bit, I'm going to expand this. I'm also going to make this a little bit easier to read. I think that should do it. So it just told me that it already found a kubeconfig file there, and it's going to merge the configuration to it. So it's merged that configuration, and it is the active cluster now. The Kubernetes client, the kube control or kubectl, can work with multiple clusters. So you can have it configured for multiple clusters, and you can choose which cluster you want to work with. So once I ran that command, it has already selected this particular cluster by default to work with when I use kubectl command. So let's run a command. Get nodes, like the wide output, and let's see what comes up. So it's showing me, okay, I have 6 nodes here. They're all running Oracle NX 7. The kernel version is kind of a giveaway, right? Because here I can see that, hey, this is an ARM node. That's an x86 node. That's an ARM node. That's an x86 one, and so on, right? So I have 6 nodes here. 3 of them are x86. 3 of them are ARM. And I am connected to my cluster at this point, right? Now, for the remainder of this workshop, right, I have created a set of instructions and the application definitions in a GitHub repository here. So I'm going to be using that, and you should be able to follow along as well. I've also provided a quick command here that you can run to quickly get your nodes to identify themselves. So that'll basically show you which ones are ARM and which ones are x86 or AMD 64. So these nodes are named by their IP addresses. So you will notice that the name of this node is 10.0.10.11, and the other one is 10.0.10.161, and so on. Those are the names of the nodes, and that's the architecture. Now, let's start by creating a very simple application, right? So like I mentioned before, for this simple example, I'm going to be using Tomcat. Tomcat is a very popular Java web server or Java web container that can run Java-based web applications. And the unique thing about Tomcat is available for ARM64 architecture as well, and it is provided as a manifest list image. So when I'm running Tomcat and I just say, hey, I want the image Tomcat version 9, the client and the repository will coordinate whether I'm going to get the x86 version of Tomcat or the ARM version of Tomcat. Excuse me. So let me quickly go through this manifest. And when we build Kubernetes applications, this is how we describe our applications. And the central notion with Kubernetes is that, once you have a description of an application like this, Kubernetes keeps track of this description, and it'll always try to ensure that whatever I've described in this description is true. So let's quickly go through this, right? So initially, you will see some API versions and a kind. This is the kind of object this is. It's a deployment. They manage larger scale deployments. And this is the definition for it. So in the definition, I'm saying that I need 6 replicas of this application. So that tells Kubernetes it needs to run 6 containers or 6 instances of this particular application. And it's going to attach some labels to it, and there is a specification for how this application needs to be structured. We will touch this in a little bit, but let's look at the containers first. it basically says that, okay, my application is made up of this following containers, and it has just one container in it, and that container is Tomcat. And the image that I'm going to use is Tomcat 9. And I'm also going to say that it's going to open port 8080, and it's also going to mount a particular volume. And there is a volume definition that is coming from a config map. And then that is the end of that definition for the deployment. Within the same file, I'll also have a service definition. And here I'm basically saying I want to expose port 8080 of the target application onto port 80. And I'm going to create the service, and the service is of type load balancer. So earlier when we talked about the Kubernetes components, we kind of touched upon the cloud controller manager. So when OKE sees this definition, it knows that, oh, I need to create a load balancer to fulfill this service. And OCI or OKE is going to create an OCI load balancer. If you were to deploy the same manifest in AWS, it would look at this same definition and it would create an elastic load balancer for you, which is the AWS version of a load balancer. So you're really shielded from these vendor specific details because Kubernetes lets you specify in generic terms what is it that you need, and the cloud specific details are filled in by the cloud controller manager. Now let's come back to our deployment and talk about the topology spread constraints. So here, I'm basically saying that there needs to be a topology called kubernetes.io/arch, and I want to spread my containers based on this key. Let's take a minute to understand that, right? Every Kubernetes node will have labels attached to it. In fact, most Kubernetes objects have labels attached to it, right? So let's see the labels on our nodes. We have 6 nodes, and all 6 of them have, that's a little hard to read, but let me just pick a random node here, and they are comma separated values. So they have labels like kubernetes.io/os and kubernetes.io/arch, right? So here in this node, this is an AMD 64 node. So what my definition says here is that for every distinct value of kubernetes.io/arch, I want to spread my pods evenly across this. So this is a great way to achieve or to introduce workloads to a new architecture or a new OS or any kind of configuration by maintaining a specific ratio. In my case, the ratio is 1:1. But this is a way in which we can assign workloads to specific nodes or, in broadly speaking, different categories of nodes, right? There are many other ways inside Kubernetes to do similar things. The most simple one would be called a node selector, which basically says, you're saying, I want to run these applications on nodes with a specific label on it, right? Or you could say use node affinity. You could use stains and tolerations. There are many ways that Kubernetes exposes where you can control how the scheduler picks the nodes to run your application, right? Now, in this example, I'm using the topology spread constraints. So let's copy this whole manifest and bring it into our environment here. So that's a here doc. So you can just copy paste it, and it's going to create a file called Tomcat for us. Let me just remove that file really quick because we're going to download it again the next step. So once we have our definition of our application created, right? Let's actually start deploying it. To deploy it, we actually need the actual application as well, alongside the Tomcat image. So I'm going to download the application. I'm going to import it as a config map. Uh, Again, I'm bringing in an application as a config map for the purposes of this lab. That's not really a good way to deploy applications into Tomcat. Just want to call that out. This is just a quick shortcut I'm taking. Don't do that in real life situations. So now that we have the now that we have our um, application definition created and our config map created, we have all our ingredients for our application, right? So let's tell Kubernetes to apply this configuration, which will tell Kubernetes that it needs to create this application, needs to have 6 instances of this application ready. It needs to be using this image, and it needs to be spreading those instances based on this constraint. So let's try that. Okay, so it's created a deployment and it's created a service. Let's look at the status of these two now. We can get the status and see where we are with it. So we have the service that is created. We have 6 pods running, and we need an external IP address so that that load balancer is getting created inside OCI right now. We should probably be able to see it. And if we go to networking and load balancers, we should be able to see that a new load balancer is being created. Yeah, a new load balancer is being created for us. So once that load balancer is fully ready, we should be able to see that. Okay, that load balancer is ready now, and we have a public IP address here. Before we go and check out the application, let's make sure that our application is making use of both the node types, right? So let's go ahead and run a command. That's basically going to get us all the running nodes and where these pods are running. So let's go back again and figure out our nodes once more. So we know what's running what. Okay, so we have 2 pods running on .11, and .11 is an ARM-based node. We have 1 pod running on 161. 161 is AMD, and 1 on 243. 243 is ARM, and 2 on 42, and 42 is AMD. So Kubernetes has fulfilled our constraints by running 3 of the pods in x86 machines and 3 of the pods in ARM-based instances. So we have an even spread, right? And this is a great way to introduce ARM to our ecosystem, because when we think about it, when we are introducing a new architecture to our enterprise application ecosystem, and we want to slowly introduce it. I mean, I've gone a bit aggressive here and did an even split, but I could have said I want 80% of my workloads still on x86 and 20% on my ARM. And if I start noticing a bunch of errors or performance issues or anything like that, I'm generating all the metrics, all the data that can help me troubleshoot that and also fix my application if it needs to. And then Kubernetes can quickly back it off, right? Kubernetes can quickly take those 2 or that 20% of the ARM nodes offline and just go 100% on x86 if I'm seeing problems, and then slowly introduce it again, right? And doing that over time, we can go from 20% of ARM nodes to 40% of ARM nodes, 60% of ARM nodes, and slowly taper off, right? Because the cost advantage and the power advantage with ARM, and it's quite staggering, right? Now let's come back. So here we have achieved a even spread. Now, before we move on, let's also quickly take a look at the application itself, right? So the application was running on this IP address. So I should be able to hit that IP address /sample. That's the context for that application. Yeah, we have an application running there now. And this is a traditional hello world example. And like we saw, we're basically running it as an event spread. Now we could go and edit that and say, I wanted just, I don't know, 9 replicas, and Kubernetes will make that happen for us as well. So it's pre-configured that deployment, and the service is unchanged. Let's go and take a look at the pods again now. We'll have more pods running this time, and we have more workloads on 161, 42, and one new one in 190, right? So it is still gonna keep an even spread. I mean, 9 is an odd number, so there will be a skew of 1, which you probably saw in our definition. It basically said, I'm allowing a max skew of 1, and if it is unsatisfiable, then do not schedule the pod, right? So if for whatever reason Kubernetes cannot find a way to keep the spread the way I want it, then it's not going to schedule that pod. With that hello world example out of the way, let's move on to something a little bit more interesting. Let's move on to something a little bit more, fitting for these technical conferences. I basically think that no conference is complete without a WordPress example. So let's try to run WordPress. You can basically find the manifest for this inside the Git repository. So you can just clone it. And again, the cool thing with the Cloud Shell is that it comes with all the tools included, including Git. So I can just do a Git clone, and I have the repository cloned now. And I'm looking at that repository, and here I have a folder. If I can scroll fast enough, called manifests. So this is a much better, I would say, or much more realistic type of application deployment or a deployment manifest. The Tomcat example was very simplistic. I mean, it was very hello world-ish, right? So this is slightly bit more realistic. We are running 2 separate types of things here. We're going to run a database with MySQL, and we're also going to run WordPress itself. Let's take a look at each of them, right? So it's going to run MySQL is going to run as a headless service. I'm not going to go into like details of headless services, but it's effectively something that other pods can use without exposing it anywhere else. That's a very mild way of putting it. We also have some MySQL configuration. Like I said, a container and its configuration can completely be encapsulated in these deployments. So, you can get exactly what we want any number of times. It's completely repeatable, completely portable, right? It's also going to use some new objects here. We have a persistent volume claim. Persistent volume claims are things that generate storage. So I'm going to be using a database. So obviously I need to store that data somewhere. So objects like these in Kubernetes can create storage, storage volumes within the cloud provider. So it's going to create a persistent volume, and that's going to be based on the OCI block storage. And then we see the actual deployment itself. You'll see that the deployment is slightly bit more complex here. You'll see all the elements that we saw earlier, but the actual container or the actual pod spec itself is slightly more complex. We are using a very specific version of MySQL. And there's a bunch of parameters that are being passed into that MySQL. And one key thing to note here is that we're not going to be using any passwords or hard-coded passwords anywhere. So Kubernetes likes to manage these as secrets. So that's what we're going to use, and we're going to generate a secret at the time of creating this. And similarly with WordPress, we have the service, but this time this service is load balancer, right? Because we want to expose WordPress to the internet. We're gonna run a blog site, right? So this will also use some storage. It'll also have its own deployment definition, and that deployment definition includes all the parameters for WordPress, as well as how to connect to that MySQL host and what usernames and passwords. Again, nothing, no specific things hard-coded here, but it's using the Kubernetes constructs to do that. So let's go ahead and deploy WordPress on our mixed or heterogeneous cluster here. Before we do that, I just wanted to quickly call out, right? This deployment did not call out any specific architectures. So Kubernetes is not going to care where this is going to get scheduled right now. Right now, after this is done, if we have remaining time, we will look at how to assign this workload to a specific architecture. But right now, the way this manifest is written, it is not using a node selector or topology constraints or anything of that nature that tells Kubernetes, hey, I want this particular workload to be deployed on an x86 or an ARM type of architecture. I'm not saying anything like that. So Kubernetes is free to choose wherever it sees fit to schedule and create my pods. And the beauty of that is whether it picks an x86 node or whether it picks an ARM node, the right container images and the right configuration is going to get pulled with the same application definition. So let's run that. So y-k maybe I have a typo there. Let me see. Let's go and try it again. Okay, so it's created the config map, it's created the secret, it's created the MySQL and WordPress deployments, the persistent volumes, and all of that, right? So we can just watch so that's a whole bunch of resources. I'm gonna watch the creation of the pods, the services, the deployments, the persistent volumes, the persistent volume claims, and I'm gonna just keep watching that, right? So we have a bunch of the containers already running. Oh, actually, these are the Tomcat containers. We have the WordPress containers and the MySQL container just getting created. We have the WordPress service that's already created. And we have our storage volumes already provisioned. So we're just now waiting for the containers to start running, and the containers are running at this point. So let's go ahead and check out our WordPress website. So that's the external load balancer that we created for it. And we should be able to go and say, and we are greeted with WordPress. So let's quickly set up WordPress. As you can see, I've done this a couple of times before just to make sure that it actually works. Let's use some simple password because I'm going to destroy this immediately. Don't do this ever. that has to be the most popular password in the history of passwords. Okay, so let's set it up. And we are done. You should be able to log in now. And we have a blog site. Let's, maybe customize it a little bit. Let's activate a slightly different theme. And let's get rid of that. Yes, we have a fully functioning blog site from Dev Summit. And we have all our resources created. And let's quickly look at where Kubernetes decided to run our applications, right? So I had a command here that would give us the pods where it's running. So the Tomcat containers are making it a little bit harder to read that definition. So let's actually undeploy Tomcat. Oh, I'm inside the. Okay, so that entire definition was contained inside that manifest. So it's going to deploy all the pods. It's going to destroy the OCI load balancer it created, and all the resources are going to get cleaned up. So once that's done, we can go and check our pods again for just the WordPress and MySQL server. I mean, I can already tell that WordPress is running on 10.11. WordPress is running on 10.11, and 10.11 is an ARM node, and .19 was another ARM node, right? So what Kubernetes actually chose ARM nodes for both my MySQL and WordPress containers. And I could go in and add a annotation or a node selector there to pin one of these to an x86 machine if I wanted to. But it just goes on to prove that, moving to ARM-based servers for your enterprise workloads, when you do it with Kubernetes, it makes it a whole lot easier. Okay, I'll wrap up there and maybe open up for questions. If there are no questions, I'd quickly like to wrap up with, to get more info on, what Oracle's doing with ARM, you can head over to developer.oracle.com/ARM to get more insights into all the other ARM initiatives that we're doing. There's a whole ton of stuff from GraalVM, MySQL, and our internal services that are focused on ARM. And also, there is an ARM accelerator program that Oracle's running, which effectively gives a much longer trial period and a large amount of credits to open source developers, universities, and industry partners who want to develop specifically for the ARM platform. Right. So head over to go.oracle.com/ARM accelerator, and you'll be greeted with a form where you propose your project for that. I mean, the only restriction is it needs to be based on ARM, and it needs to contribute to the ARM ecosystem. And as long as it does, Oracle is happy to support you or your startup in an incubation mode. I believe the best ways to get in touch would be through the email addresses that we have provided or through the GitHub repository. So if there are specific asks on the lab itself, feel free to raise an issue on that GitHub repository and we will respond to you. Or you can always reach out to us directly through our email.
Is there was there anything else you want to show on the dashboard at all, Jeevan? haven't got any other questions coming through, so there is
Sure.
anything you want to spotlight. We've got a bit of time left, so
Yeah, I mean, on the dashboard, we can go and maybe take a quick look at the other cluster that we've been creating. So let me just exit the Cloud Shell really quick here. And we should be, okay, let me just reset this. That's a little bit better. Um, so we can go and go back to OKE. At the beginning of this lab, we created a cluster, which is obviously available now. And inside that cluster, we should be able to see that there's a new node pool. You can go ahead and add another node pool. So this is what you would need to do in order to add some x86 capacity as well to your nodes, right? So um, so creating a new node pool, it's going to add more capacity to this cluster. Actually, let's name it something else. So the node pool one should be able to. Okay. To yeah, I have to select what availability domains I need this. So let's quickly pick the domain and placement configuration. I'll place all the nodes in the same availability domain, and that should get me a new node pool. And this time, the second node pool is x86 based, and the first one is ARM based. Um, the pool becomes immediately active, but you'll notice that the instances are being created. So um, as soon as the pool becomes active and now the instances are getting created, you will notice that in the um, compute instances side as well. I have a lot of compute instances here. So this is going to be a very long list for me. So yeah, so this is, these are the three nodes that we are provisioning right now. And we'll just go back to OKE, and we will see that once the nodes get provisioned, they will start updating their statuses here. So the one of the nodes is created, and right now we are installing and setting this node up um, for addition to that Kubernetes cluster. So once the other nodes get created, they will also start installing the Kubernetes components on that node, like the kubelet and the kubeproxy, and they will dial back home to the control plane. And once the control plane realizes that there are three new nodes available, it will make sure that it keeps track of these three nodes and make it available for scheduling. While that is happening, I can also show something really interesting. This is just a coincidence that, like the cluster that we used for our example here is actually one version behind. The latest is 1.20.11, and the version that I was using is 1.20.8. So one thing that is really quick that I can show you is I can actually upgrade this cluster right now. And cluster upgrades are completely non-blocking. There's no interruption whatsoever. So I'm going to upgrade this cluster, and it should not impact the workload running on it at all. We have our WordPress website running here, and it's not going to get impacted at all while the cluster is getting updated. So this is because the control plane that OKE provides for its clusters is highly available. So what's happening on our control plane right now is we are doing a rolling update on the control plane. So we're migrating to 1.20.11 node by node, while the nodes are remaining in service. So the cluster is completely available during the whole upgrade process, and the workloads are not interrupted, but we're upgrading our cluster. And that should be also enough time to go back and see our node pools. And pool 2 should be, is hopefully, oh, it's still updating. So this could take anywhere from 3 to 5 minutes, um, depending on the shape and the capacity and compute capacity available on that shape. So uh, it could take a few minutes, and once it's done, it will the nodes will become active, and once they are active and available, our Kubernetes control plane would be able to see it. Um, we can go and access this cluster right now if we needed to, and also deal with the 3 nodes that we already have. And once the other 3 nodes are bought in, we will basically have a total of 6 nodes on this cluster as well. Let's quickly go and check our upgrade status. The upgrades will also take a few minutes, but like you see, it's not going to impact the workloads at all. So
Awesome.
we can go and also maybe access this cluster and make sure that um, we are able to see everything. Let me bring up the Cloud Shell again. Okay. Let me now switch over to this cluster. This is a new cluster that we're using. So now this is my active cluster. So I could say and I should be able to see. Looks like our of the 6 nodes, 2 of our x86 nodes have been created now. So maybe in a couple of more seconds, we should be able to see all 6. Yes, we now have 6 nodes in the new cluster as well. So as and when these nodes are created and registered with our control plane, they become available to the Kubernetes cluster for scheduling. And now we have a equivalent cluster that we just created as well.